The basic version of Bayes' formula that we learned is a special case of a more general version. The basic version involved an event A and its complement. The more general version involves n events, which we'll call A1 through AN. So let's let S be the sample space. And let's let A1 through AN be events such that their disjoint union is S. So this disjoint union, the union signs with the dots in them, mean A1 through AN are mutually exclusive you take any two of them, they have no intersection, as long as we take two different ones. And they're exhaustive. Their union is all of S. So here's a picture. If this is S, then we're breaking S up into pieces. Such that when we put them together, we get all of S, and no two of these pieces overlap. No two of them overlap is called mutually exclusive. Putting them all together and getting S is called exhaustive. We've got everything in here and no two regions overlap. Now let's let B be an event. And let's suppose that the probability of B given AI is easy to find for all I. So B is some event in here. And suppose we want the probability of, say, A1 given B. So this is the opposite order of the conditional probabilities that are easy to find. Then the probability of A1 given B equals probability of A1 times probability of B given A1 divided by probability of A1, probability of B given A1, summed up to probability of AN, probability of B given AN. So our basic version n is equal to 2. A1 we just called A, and A2 we called A complement. A and A complement are mutually exclusive and exhaustive. They take up all of S and they don't overlap at all. So this formula is the general version of Bayes' formula. Let's look at the reason that it's true. The reason is basically the same as for the basic version. So we want probability of A1 given B, and that's the probability of A1 and B over probability of B. Now B, if we look at it, is a disjoint union of A1 and B, A2 and B, A3 and B, up to A, N, and B. So that means that the probability of B is the sum of the probabilities of all the pieces added together. So probability of A1 and B plus up to probability of A, N, and B. Now probability of AI and B for any I, including 1, is the probability of AI times the probability of B given AI. So if we replace the probability on the top with probability of A1 times probability of B given A1, that's the numerator we have here, and if we replace probability of B by this sum, and each summand by probability of AI times probability of B given AI, that's exactly what we have on the bottom here. So that's where the formula comes from. Alright, so now let's do an example. I'll keep the formula down here so we can look at it. Alright, let's say we have 6 cards, and they have solid colors on both sides. And those 6 cards are a card that's red on both sides, a card that's white on both sides, a card that's blue on both sides, and then one that's red and blue, one that's red and white, and one that's white and blue. So given these 3 colors, red, white, and blue, these are all the possibilities for cards. We've got all 6 of these cards. Let's say one card is placed on the table. If a red side faces up, what is the probability that a blue side faces down? Alright, so to set this up, let's come up with notation for some events that we need. So I guess this is good notation for which card is on the table. It's either going to be the red card or the white card, etc. And let's let our up arrow be the event that a red side faces up. So in terms of this notation, we want the probability of having the red-blue card given that a red card is facing up, a red side is facing up. Now if we knew which card we had on the table, it'd be easy to compute the probability of red facing up. So probability of red facing up given a red-blue card is 1/2. That's an easy problem. But the probability we have, the conditional probability we want, is a little bit harder to find. A natural guess is if we've got a red side up, what are the possibilities for what could be down? It could be a red-red card, it could be a red-blue card, it could be a red-white card. So given those 3 cards, if we believe that the cards are all equally shaped and weigh the same and feel the same, it might be natural to guess 1/3, but this isn't quite correct. So let's use Bayes' formula carefully to figure out what the conditional probability we want is taking advantage of the fact that if these events were switched, the conditional probabilities would be very easy to compute. So again, we want the probability of having the red-blue card given that the red card is facing up, which is the probability of having the red-blue card and red card facing up over the probability that the red card is facing up, the red side is facing up. Normally I'm not writing intersection between two events, but since this event has a name which is two capital letters, and one of them is this, I'll write the intersection just to separate the two events. Alright, now in Bayes' formula, remember the top numerator really is probability of A1 and B, and the denominator is probability of B. So let's, here we've got RB and R up. Let's separate this probability of B, probability of red side facing up, into all the possibilities. So probability of getting the red-blue card and red faces up over probability of, we could get the red-red card and red faces up, or all the ways that red could face up are red-red, red-blue, probability of the red-blue card and red faces up, plus probability of the red-white card and red faces up. Now let's rewrite these as probability of getting the red-blue card and the probability of the red side facing up, given that we have the red-blue card. That's easy. Probability of the red-red card times probability of the red facing up, given that we have the red-red card, plus probability of the red-blue card, probability of red facing up, given that we have the red-blue card, plus probability of the red-white card times probability of red facing up, given that we have the red-white card. Alright, so we've got 6 cards in the deck, and we'll assume that it was shuffled well and they all feel the same. So the probability of any card is going to be 1/6. So the probability of 1/6, so the probability of having red-blue is 1/6. If we know that we have that card, the probability that the red side faces up is 1/2. The probability of getting the red-red card is 1/6. And if we know we have the red-red card, the probability of red facing up is 1, of course, because both sides are red. The probability of the red-blue card, as we said, is 1/6. Probability of red facing up, given that we have that card, is 1/2, because one of the two sides is red. Probability of the red-white card is 1/6. Probability of red side facing up, given that we have the red-white card, is 1/2. So before I multiply this out, I guess I could divide the numerator and denominator by 1/6, because we've got 1/6 in every single term here. So I guess this is 1/2 divided by 1 plus 1/2 plus 1/2, which is, if we multiply everything by 2, I guess I can get rid of the formula now. This is 1 over 2 plus 1 plus 1, which is 1/4. So indeed the probability is not the same as what we would have guessed. because we saw three possibilities of a card that could have red on one side. So it's actually 1/4. Maybe one intuitive reason to understand why it's 1/4 rather than 1/3 is that when we see the red card, the red side of a card facing up, there's really four ways that could have happened. It could be the red side of the red-white card, the red side of the red-blue card, or it could have been the first red side of the red-red card, or the second red side of the red-red card. There's really four different ways that we could have seen red facing up. The end.